This is a short movie of us exploring Blockcerts. So Blockcerts is something created by MIT where they've extended the Open Badges JSON schema to include a system for verifying batch releases of badges on a blockchain. So here we did an experiment with some of our students on the Summer of Code course, and they earned some badges, and we've used that data as part of our exploration of the Blockcerts concept. So this screen is just a way to visualize the Blockcerts concept. So here, if I pick student 2, for example, there's all the 10 badges it was possible to earn on the Summer of Code course. And we're going to take just one of those badges and look at it in more detail. So what we've done is we've created the badge images with the Open Badges JSON inserted into it, and we've also added in the Blockcerts extension to the Open Badges schema. And we're going to explore what all those parts are and how you verify the badge with this system. So here we've got all the different badges, but let's just pick the first one and look at it in more detail. So basically the badge is an image file, and here's its name. And embedded at the bottom of that image file is this entire section of JSON. This is all the JSON altogether that is embedded in there. And this large section in the middle is just, it actually has a base 64 encoding of the image file itself, so the student can't alter the file. So that's everything that would be extracted from inside the ping file. Now let's look at just the Open Badges part of the JSON to begin with. This is it in its raw form, so unprettified. Now the important thing about how this system works is that it all works around hashes. So the concept of hashing is that you take a given file or string, you run it through an algorithm, and if the file or string are exactly the same, the output will always be the same. If you make even a single character change in the file or the string, you'll get a different answer. So we can demonstrate that with this example. So if I calculate the hash for the contents of this box, that's what we get. So that would be the hash of this certificate. If I make a change, let's make this, take the M off motivation there, and I recalculate, and if you keep an eye on this bottom number, you'll see it becomes a completely different number. And if I undo that change and recalculate it, we go back to the original number. So the whole validation concept for this batch releasing of badges is built on hashes. This is the first hash of a series of hashes that we're going to look at, and that's the hash for the JSON. Now that's the top half of the original embedded JSON. The bottom half is the main extension that was added by MIT in the Blockcerts concept. So the various bits, and I've color highlighted the different aspects, and I'll keep the color coding down just so you can trace it a little more easily. So you'll see that here it says what type of proofing this is, and it's Merkle proofing, and I'll show you that later, and that it's an extension to the original Open Badges schema. So the first piece of information to look at is the hash of the badge, and that's the one we've just calculated up here. The next piece of information is the Merkle root. So that's the hash that represents an entire batch of badges that are being released in one go. This is the transaction ID on the blockchain where that root hash is stored. And this type says that we're using Ethereum to store this, so that it can either be Bitcoin or Ethereum in this system. And these are the elements, these are the hashes that are required as part of the proofing that a given badge belongs to a given batch. So we're going to look at all these in more detail now. So let's look at the transaction first. So that's the purple thing. So this is a unique identifier for an individual transaction on the blockchain. So let's go and get the data for that. And let's look at it in more detail. So if you ask for the transaction data for this transaction, you get something similar to this back. And the two key bits in here that are important are the hash, to say it matches, this is the data for this transaction, right? And then the input. And the input is the root hash, and that will match here, E9, E9. Okay, so you can see the root hash was put onto that transaction. So these two pieces of information inside the badge are correct. They match up. And we know that this is the target hash because we rehashed it here. So those three pieces of information are correct. So now we've checked that that actually got put on the blockchain with the root hash as it said inside the badge. Let's look at how you calculate that that target hash, which is the hash of an individual badge, is in fact part of this batch. Okay, so we now need to show how that calculation is done because somebody needs to be able to take the JSON, this JSON at the bottom of the image file, and prove that the information in the main badge data here is the information that was issued and put onto the blockchain and hasn't been tampered with at all, so it's correct. So here's the Merkle proofing part. So for the purposes of this demo, we've just done it in batches of 16. We're taking 16 badges at a time from the summer of code and calculating a root hash for them and putting it on the blockchain. So we've done that. You can pick different numbers, and the good thing is that you double the number each time, but you only need to then go up one level in calculations. So this little list wouldn't grow that long for quite a large batch set if you wanted to really release a whole 1,000 in a go or something. And the whole purpose of batching it is because obviously mostly these things are being done on the live public Ethereum or Bitcoin blockchains where there are cost implications. So if you wanted to put a hash on for every single badge, that could get expensive. Whereas if you can batch release them and put a single hash but still prove a given child hash was in that batch, then you can release one hash for an entire class or an entire year even. That's why this process was invented, to make it cheaper to do on a public chain. So let me explain what you're going to see, and then I'll press calculate, which will animate the process, and then I'll probably explain some more and press it again so you can understand what's happening. So basically we have the hash of one of these, we have a path up the tree already, and we have a potential route. These are the pieces of information we start with. So when I first press calculate, it'll fill those in. Now it's going to put these two strings together, hash it, fill it in next to the other one, and follow the process all the way up until it reaches the root. And that matches. So let's just look at this a little more in the color coding and the here in the color coding. So what you'll see here is that in the proof you have right, left, right, right. And this always starts from the very bottom of the tree up. So if you look here, we have the right hand side, in the next pair the left hand side, in the next pair the right hand side, and in this pair the right hand side. So that's how we got the right, left, right, right parts. And this is where we filled in those numbers here for right, left. So 529 is 529 here. So that's how we fill them in the calculation on the way up. So what you do is you take the two string representations, the two hashes here, you put them together as one long string, and then you hash that result. And then you feed that hash, so you can see the hash that's come out of this new string gives you this, and then that's fed into the next level against the bit you already have, so that's here. And then you repeat the process. You put the hash, those two hashes together as one, you calculate their hash, and you feed that up into the gap on the next level. And that's what you do again and again. And if you do that all the way up, you'll reach the root. So let's clear it and do that again and watch it happen this time. Now, if you imagine different badges at the bottom here in the batch will have different paths up the tree. So if we picked a different badge, it would have a different looking profile. So let's do that just to show you. So let's pick badge 2. We don't need to go back through all this data. Let's look at the left, right, left, left. You see this one's different. Left, left, right, left. So its profile, when you build it, will be different. So now it's over here, and you're filling in this branch in the tree until you reach the root. So this process can be repeated for every single one of these badges. It'll have a different path up the tree. You'll store a different set of these green proofing hashes, and it'll allow you to recalculate that this child badge, this individual badge hash, belongs to this root that was put on the blockchain. So hopefully that's explained how the Blockcerts method works.